All right, welcome back. So we're on to 2.2, which is higher exponents. And by higher exponents, we mean higher than squared that we've talked about so far. So we know a to the second power, we can call a squared. The reason why we call it squared is because if we draw a square, then it would be then a by a squared. And if you did the area, base times height, a times a, that'd be multiplying a 2 times to get the area of the square. All right, it's not a great looking square, but to the third power is going to be called a cubed because, like a square, that would be the area of a cube. And a cube, we can draw a cube here. So we have a square here and a square here. You can kind of draw a little cube here if we can. Maybe not the best looking cube, but you kind of get the idea here. And we have a cube, and there's going to be an a by a cube. The base is a, the height is a, and the depth is a. So it'd be a times a times a to get the volume of the cube. So if you've done much with 3D shapes and volumes, then you would already know that it would be a cubed to get the volume of a cube, or a to the third power. So that's why it's called cubed. Anything higher than that, we don't have a fancy name for. So a to the fourth power would just be a raised to the fourth power, a to the fourth power, or you can just say a to the fourth would all work. Same thing with like a to the 20th. So a in this case here, this a here would be called the base, and then the 20 here would be the power. All right, and so what this is saying here is, we kind of discussed this in the last section a little bit, but this is saying that we're going to be multiplying 7 20 times, just like 7 times 20 would be 7 plus 7 plus 7 20 times, right? Just like that, 7 raised to the 20th power would be 7 times 7 times 7 all the way at 20 times. 20 copies of 7. All right, also another exponent fact here is anything raised to the first power is just going to be itself, because you're multiplying it how many times? You're multiplying it 1 time, so a, and then that's all you got. Not a times anything else, it's just a. So a to the first power is just a. All right, a couple other things here. So we can kind of see that if we have a, b, both to the n power, then we can sort of, it's not called distribute because this is not addition, but we can apply that n to both of those. So an times bn, or b to the n. We sort of discussed this in the last section. If we have a reciprocal here, and so we have b in the denominator here, then we would get b to the n. We did do that specifically for, I don't know if we called it b, but some variable in a reciprocal, and we said that it would be 1 over b squared, but that actually works for any power here. Any power n would be 1 over bn, and I briefly discussed that this power would actually apply to the numerator also, but because it's 1, then you can multiply 1 as many times as you want, and it's going to remain 1. All right, so power of quotient, if b is non-zero, then kind of like here where this n was applied to both a and b, this is the same way. N would apply to both a and b, which really this here, a divided by b, is the same thing as this right here, because it's really saying 1 divided by b. That's what a fraction is. So to no surprise, this would distribute to both just like, or this would distribute to both just like the fraction distributes to both the numerator and the denominator. All right, but a warning right here that it does not distribute in the traditional sense of distribution. So if we have a plus here, a plus b, we cannot distribute that squared to a and b. So it would not be a squared plus b squared. That would not work. So we cannot do that. All right, so now moving on to the problems. Go ahead and compute -4 to the third. And b is how many integers n is n cubed between -50 and 50. So basically, if n is, let's say, 1, for example, 1 cubed would be within -50 and 50. So how many integers would would qualify for that. Hopefully that makes sense. All right, and so if you're just coming back to these and don't remember, so what I usually do here is go ahead and pause the video here, try to give these problems a shot on your own, and then we'll discuss and see how close you were. All right, but moving on here. So to compute this -4 cubed, we know that these exponents are just repeated multiplication. Remember that we're repeatedly multiplying -4. We did this in the last section for squared. We multiplied it 2 times. Now we have to multiply it 3 times. So it'd be -4 times -4 times -4. All right, and so this would end up becoming, so -4 times -4 would be positive 16, right? Negative times a negative is a positive. So that'd be positive 16 times -4. So then 4 times 10 would be 40. 4 times 6 would be 24. 40 plus 24 would be 64. And positive times a negative would be a negative. So if you notice, if you remember in the last lesson, if we had something like -2 squared, that was going to give us a positive number. That would give us a positive 4. And we said that -a squared would give us a squared. But in this case, we get a negative number. So if we have a -4 cubed, we get a negative number. So this is the cube of negation. In the last section, we have the square of negation. This is the cube of negation. And if we cube a -a, then we get -a cubed. Remember, this isn't necessarily the same. If you say, like in the last lesson, if we did -a squared, that is not the same thing as saying -a squared, because you do exponents first in order of operations. So you would do this part first and then tack on the negative. In this case, you are multiplying with the negative multiple times. So this is not the same thing. In this case, it does become the same thing because you know that your final answer is going to be a negative. So either way you do it, you're going to come up with the same answer. All right, so for the second part, so for how many integers n is n cubed between -50 and 50? All right, so if you start here with 0 cubed. 0 cubed is going to be 0. So we know that that's going to work, right? That's in between -50 and 50, so 0 works. How about 1? 1 cubed is going to be 1. That's between -50 and 50, so that's going to work. How about 2? 2 cubed, 2 times 2 is 4, times 2 is 8, so that's going to work. So 2 also works. How about 3 cubed? 3 cubed would be 3 times 3 times 3, so that would be 9 times 3 would be 27. That works, so 3 works. How about 4? So let's see. So let's do 4 times 4 times 4. 4 times 4 is 16. 16 times 4, we already did this one here, is 64. 64, and that is not within -50 and 50. So 4 is not going to work. So we have 0, 1, 2, and 3. We also need to remember the negatives. So we have -1, because we know that -1 cubed is going to be -1. -2. -2 cubed is going to be -8, and we'll have -3. And -3 cubed is going to be -27. -4 cubed would end up being -64, which we have right there, and so that would not be between -50 and 50. So how many integers do we have? We have 1, 2, 3, 4, 5, 6, 7 integers between -50 and 50. All right, so explain why -a in parentheses to the fourth is equal to a to the fourth, and explain why -a in parentheses to the fifth equals -a to the fifth. So take a second, see if you can figure out why that is the case. All right, so if we multiply -a out 4 times, we get -a times -a times -a times -a, right? That's what -a to the fourth is. All right, so now we can extract out all these negatives. We have 4 of these negatives, so we'll pull them all out in front. And then we're left with these 4 a's, a times a times a times a. Well, a negative times a negative is a positive, those cancel out. And a negative times a negative is a positive, so those cancel out. So then we're left with a to the fourth. All right, but here's b. Same thing, negative a times negative a times negative a times negative a times negative a, 5 of them. Now we pull out all the negative ones. Negative times a negative is a positive. Negative times a negative is positive, but look, we still have one negative left. So we have a to the 5th, but it's going to be negative a to the 5th. All right, so power negation, let a be any number, let n be a positive integer. If n is even, then we're going to get a positive number. If n is odd, then we're going to get a negative number. That is, if we have a power that, if we have a base that is negative, and our n is odd, then we get a negative number. Hopefully that's clear. So if we have something like negative a to the, we already know squared is going to give us positive, because negative times negative is positive. But what if we have negative a to the 22nd? That's going to give us a positive. But if we had negative a to the 23rd, we know that that's going to give us a negative, because it's an odd number. I like to remember that just by thinking about squared, because squared is the easiest to remember, because we know that a negative times a negative is a positive. So we know that squared is going to give us a positive number. So then that's a good reminder that all even numbers will give us a positive number. All right, so now evaluate this one. Go ahead and give that a shot. So with our order of operations, we're going to want to evaluate our parentheses first. So let's go ahead and do this 5 squared. So that 5 squared is going to be 25. And so that's going to be negative 1 to the 25th. Well, 25 is an odd number, so there's going to be negative 1 to the 25th, and we know that that's going to give us a negative number because that's an odd exponent. So the first term is going to end up being negative 1. The second one here is going to be 1 to the 25th. So 1 multiplied out 25 times is still going to just be 1. So it's going to be negative 1 plus 1, and that's just negation. That's going to give us 0. All right, addition and multiplication are commutative. That means a plus b is equal to b plus a, and ab is equal to ba. So both multiplication and addition are both commutative. So we explore whether or not exponentiation is commutative. So we're going to try 3 to the 4th and 4 to the 3rd to see if those two are the same. So do you think those two are going to be the same? All right, so go ahead and give that a shot. All right, so the first one here is 3 to the 4th, so 3 times 3 times 3 times 3. 3 times 3 is 9, 3 times 3 is 9, so then we get 2 9s. 9 times 9 is 81. All right, so 4 times 4 times 4. We've done this one a few times. 16 times 4 is 64, so they are not commutative. Okay, addition and multiplication are associative. So let's explore whether or not exponentiation is associative. So these are the same numbers, 2, 2, and 3, and 2, 2, and 3, and just going to be a different order of how we do it. So go ahead and give this one a shot and see if it's associative. All right, so parentheses first for this first one here. So we're going to do 2 squared, which is going to be 2 times 2, which is 4. 4 to the 3rd, again, is 64. We've done that one a few times now. All right, so now we'll try for b. So now, again, we do the parentheses first. So 2 to the 3rd is going to be 8. 2 times 2 times 2. Don't accidentally say 6. It's not 2 times 3. It's 2 times 2 times 2. So that's going to be 8. So it'll be 2 to the 8th. And then we've got 2 times 2 is 4. Times 4 is 8. 2 times 2 is 4. Times 2 is 8. Times 2 is 16. So 4 of these 2's are 16. So then the other 4 is also 16. And we've got 16 times 16, which is 256. All right, so these two are not the same. 256 and 64 are not the same. So that means that exponentiation is not associative. So this is kind of a copy and paste of a small image here, so I don't know if you can read it, but this is 2 to the 2nd to the 3rd without any parentheses. So we need to decide how we're going to do this. What's the right way to do this? because we don't really have a rule in our order of operations. We say exponents first, but which is the exponent? So do we do 2 squared first, or we do this 2 cubed first? And the correct way to do this actually is to work from the top to the bottom. So you would do 2 cubed first, and then it would be 2 to the 8th. So that's the correct way to do this one, and that's the way we'll be doing it going forward. You won't really see it written like this very much because it's not super clear what you want to do. And in math, we're not trying to trick you. So we're not going to give you stuff like this just to trip you up and trick you. If it's something that could be a little bit confusing and that someone might not be too sure about the proper way to do something, then we'll generally just clarify and then put the parentheses where it would make it more clear. Okay, let a be any number. Explain why a cubed times a to the 5th is equal to a to the 8th. All right, so go ahead and write this out. I probably didn't give enough time to pause there, but hopefully this one isn't too challenging here. So let's just write these out. So a cubed we know is a times a times a. A to the 5th is a times a times a times a times a. If you put that all together, that's 8 a's, or a to the 8th. So product of powers, you notice here, I don't know if you could tell that, but a to the cubed times a to the 5th, that's 3 and 5 we have here. So it looks like they were added together. And in fact, you can do that. Anytime you multiply 2 exponents together with the same base, it has to have the same base, then you can add the exponents together. So a to the m plus n. Okay, so now express this as a power of 5. Meaning you're going to have 5 as the base, and then what's the exponent going to be? All right, so let's go ahead and write this out. So you probably noticed that these are all the same, right? How many of these do we have? We have 5 of them. So we have 5 times 5 to the 17th. Well, if we have 5 times, remember what 5 to the 17th is 5 times 5 times 5 times 5, 17 times. So now we just have another 5 that we're multiplying in with that. So now we have 18 5s multiplied in. You can also consider a 5, same thing as 5 to the first power. Remember 5 to the first, or anything to the first power is just that same thing back, right? So a to the first power is just a. So we can convert this to an exponent if you want to just make this a little bit more clear. Say 5 is equal to 5 to the first power. And now we know, same base, 5 and 5. Now we can add the exponents, 1 plus 17. So it's going to be 5 to the 18th. All right, so now we're going to try some division. So 9 to the 7th divided by 9 to the 3rd. And explain why that is equal to 9 to the 4th. This one's a little bit more tricky to do, so go ahead and give us a pause here and see if you can come up with a reason. Just try to think of this one through. If you can't figure out why this might be true, then we'll go over it here in a second. The first thing you want to do is probably think about it this written out. So 9 to the 7th would be 9 times 9 times 9, 7 times, divided by 9 to the 3rd, 9 3 times. And just think about what that could mean. It's actually probably even an easier way to go ahead and do that, but you might not have thought to do it this way, and if you didn't think of it this way, then don't worry about it. So we know that 9 to the 7th is the same thing as 9 to the 4th times 9 to the 3rd, right? Because we can, if they have the same base, we can add the exponents, so 4 plus 3 would be 7. So these two are equivalent, we know that. Let's go ahead and just convert that. So where we had 9 to the 7th, we're going to replace that with 9 to the 4th times 9 to the 3rd. So that's what we have right here, 9 to the 4th times 9 to the 3rd. And remember to keep our divided by 9 to the 3rd. That hasn't gone anywhere yet. All right, but now we can convert the division to multiplication like we've done before in chapter 1. So instead of this division, we're going to multiply by the reciprocal. So now we're going to multiply by 1 over 9 cubed. That's the reciprocal. All right, now we can use the associative property and regroup some things a little bit. So we have 9 to the 4th, and now we're going to group together this 9 to the 3rd times 1 over 9 to the third. And that you should probably recognize is going to be a reciprocal, and that's going to be the identity, or 1. So that's going to be 9 to the fourth times 1, or just 9 to the fourth. A simpler way to do that is to know that when you divide exponents with the same base, you can actually subtract them. So if you see this, we had 9 to the 7th, and we divided by 9 to the 3rd, and we had a 7 and a 3, and that 7 minus 3 got us 4. So when you do division, as long as they have the same base, once again, then you can subtract the exponents. So m minus n. There's a video here you can watch for more information on that. Okay, so you might have a sense of how to go about doing this one, but explain why 7 to the 5th to the 3rd is equal to 7 to the 5 times 3. Go ahead and give this one a shot. First of all, think about what 7 to the 5th to the 3rd really means. All right, so what that means is that this is going to be 7 to the 5th 3 times, right? 7 to the 5th times 7 to the 5th times 7 to the 5th. And we also know that we can add these exponents together as long as they have the same base. 7 to the 5th times 7 to the 5th times 7 to the 5th. Well, we can do 5 plus 5 plus 5. And there we go right there. Well, 5 plus 5 plus 5, that's the same thing as saying 3 times 5. That's 3 5s. So 7 to the 5 times 3. And that's what we're looking for right here. And we could also just do that multiplication and say that that's going to be 7 to the 15th. So when you raise a power to a power, a to the m to the n, you can multiply those powers together. So you see here, 7 to the 5th to the 3rd, we just multiplied those powers together to get 7 to the 15th. And you can always do that. So now, knowing all those exponent facts, I know we've gone through a lot of exponent facts so far, but we can use all of those tricks that we've learned to be able to solve these. So go ahead and give these 3 a shot real quick. Go ahead and pause this and try these out, and then we'll go over them. All right, so this first one right here, we have 2 to the 7th times 2 to the 8th divided by 2 to the 3rd. All right, so the first thing we can do is we know we can add those 2 exponents together. So we get 2 to the 7 plus 8. And don't forget our divided by 2 to the 3rd. So 7 to the 7 plus 8 divided by 2 to the 3rd. And remember, if you have the same base and you do division, you can subtract that exponent. So now we have 7 plus 8 minus 3. And you do that math and you have 2 to the 12th. All right, so now for the second one, we have 2 to the 6th to the 4th. Well, we know that when you raise a power to a power, you can multiply those. So that's going to end up being 2 to the 24th, right? So yeah, we have 2 to the 6th times 4, and still have our divided by 2 to the 7th. And we know we can subtract, if we have the same base, we can subtract. So we have 24 minus 7, and that's going to give us 2 to the 17th. Now to this third one is a little bit tricky. So if you weren't able to get this third one, don't worry, this one is tricky. So you can't just say 6 minus 2. And why can't you say 6 minus 2? Is because you can only do that if they have the same base, and these do not have the same base. So what we can do is we can get them to be the same base. So 4 and 8 are both powers of 2. 4 would be 2 times 2, and 8 would be 2 times 2 times 2. So this 4 would be 2 squared. Right here, 4 would be 2 squared, and 8 would be 2 cubed. So if we swap those out and use these values for 4 and 8, then we can change this equation here. So instead of using 4, we're going to use 2 squared. So we have 2 squared to the 6th instead of 4 to the 6th. And here we have 2 to the 3rd squared. Instead of using 8, we're going to use 2 to the 3rd, or 2 cubed. So we have 2 cubed squared instead of 8 squared. All right, now we know how to do this. Now we can do 2 times 6 is going to be 12, 2 to the 12th, divided by 2 to the 3 times 2 is 6, so 2 to the 6th. And now we can do 12 minus 6, so it'd be 2 to the 6th. All right, so this one here, the wording of this is a little bit confusing, so let me see if I can reword it to make it a little more sense. So it says express 11 to the 20,000th as a 10,000th power. by finding the positive integer a such that 11 to the 20,000 equals a to the 10,000. What this is saying is that find what number you can convert this to be something, some number to the 10,000. So right now we have it to the 20,000s. Let's see what number would be the base to the 10,000th. And same thing with these two problems. And then which of these three is the biggest number? So give that a shot if you can. This one's a little bit tricky. If you can't figure this one out, not a big deal, but see if you can think through this and see if you have a good idea of at least how to get started on this. All right, so we're gonna go backwards this time. So we have 11 to the 20,000th, but we're gonna go to the 10,000s. So we know that we can, if we kind of multiply with the same base, if we have 11 to the something times 11 to the something, we have the same base and we can add together those exponents. We also know that if we raise to a power of a power, we have something here, let's say m to the n, then we can multiply those together, right? So if we split this up, instead of 20,000, we know we want 10,000. So 20,000 is the same thing as 2 times 10,000. So 2 times 10,000 it would give us 20,000. Maybe we can work backwards from there. So 11 to the 20,000 is the same thing as 11 to the 2 times 10,000, right? That would still be the same thing because 2 times 10,000 is still 20,000, so these are still equal. And now that we have this, we know what we have multiplication here. That's going to be a power raised to a power. That's when we have multiplication. So we have 11 squared to the 10,000th. So what is 11 squared? 11 squared is 121. So there we go. That's our answer right here, 121 to the 10,000th. So maybe now that you've gotten that, I mean, I know I'm showing the answer already, but if you haven't already looked at the answer, or see if you can come up with the answer for these next two yourself. Maybe go back a slide, go back in the video a little bit and see if you can solve the next two now that you kind of get the idea of how to do these. But the next two are very similar. We're going to do the same thing for the next one. So we have 5 to the 30,000th, and that's going to become 5 to the 3 times 10,000. And that's going to be equal to 5 to the third raised again to the 10,000. And then we compute 5 to the third. That's going to be 125 10,000ths. All right, so then for the last one, same thing. 2 to the 70,000ths, be 2 to the 7 times 10,000. And that's going to be 2 to the 7th to the 10,000. And 2 to the 7th, if you multiply that out, it's going to be 128 to the 10,000. All right, so now for D, which is the greatest of the three? Well, now they're all to the 10,000 power. So that's all the same. So you just need to find out which base is the biggest. So 128 is the biggest base. So we know that 2 to the 70,000ths is going to be the biggest of those three numbers. And that's it. So I know that was a lot. That was a long lesson with a lot of different problems, but go ahead and see if you can try these 2.2 exercises and see if you get a hang of this. I know this was probably the hardest section that we've had so far. So any questions that you have on this lesson, feel free to ask, and I don't mind making another video to explain anything that you're not quite getting. So other than that, I will see you guys next time.